This model solution represents just one method of answering the questions. The PA solution says this solution is provided so candidates may better prepare for future sittings of exam PA. It includes a sample solution in plain text and commentary from those grading the exam. In many cases, there is a full range of satisfactory approaches. This solution represents just one approach, with commentary on some alternatives. This video gives you examples of some alternatives which help you to save time. In this video, we'll be going through the solution to the June 18th, 2020 exam PA. To begin, you'll need the project statement. You'll also need Word document and the RStudio template. I'll arrange these so that I have them both on the same screen. And to begin, I will just read through the entire project statement quickly. I'll skip over this general information for candidates because you have seen it before. The business problem. You are an actuary at ABC Insurance and have been asked to assist the marketing department. They have collected data on a completed marketing campaign for a particular insurance product. The campaign consisted of calling prospective customers. For each call, a variety of data was collected, including whether the prospect purchased the product. They would like you to advise them on future campaigns so that their efforts will be most productive in terms of purchases. Your task is to use the available data to construct a model that will generate insights into the productivity of marketing calls for the same insurance product. Your model will not be used to predict the outcome of the future calls. Instead, the marketing department wants advice regarding possible adjustments they can incorporate into future marketing efforts. So I see right away that the objective is inference rather than prediction. Your assistant has done some preliminary analysis, which are scattered throughout the supplied RMD file. And then I just read through the specific tasks and look at the point allocations. I see 8 points, explore the data, 3 points, consider the education variable, 5 points, handle missing values. So I see that's 8, 9, 10, 11, 16 points just on the first 3 data manipulation questions, 3 points on correlations, and then 7 points on PCA. And then we get into the modeling, 5 points on the GLM, 8 points just on selecting features. That implies that there's probably some complex features in this. 12 points on evaluate the model, 9 points on investigate a shrinkage method, and then 9 points on cost complexity pruning, and 4 points on choose a model, and then 20 points on the executive summary. And I look at the variables here, and I see that it looks like there's a mix of categorical and continuous variables. So let's go back up to the project statement and look at task 1. Task 1, explore the data. Your assistant has built the following charts: a histogram for I-rate, bar charts for month and EDU years, a box plot for the age distribution by different values of job, and a graph showing the proportion purchasing by age and month. Run the code to make them. So this implies that you should include all of these graphs. So let's go over to the document here. And so we're going to want to think about each of these variables. So there is going to be I-rate, month, EDU years, age, job, and age and month. And I like to just type this out in the document first so that I don't get lost when I start looking at all of the code. I see some code. I'm assuming this is just going to create all of those graphs. And I got an error saying that my R session aborted. So let's try this again. Hopefully these types of errors don't occur on your exam. Okay, so there's a histogram for I-rate, and it says your assistant has built the following charts. So I don't need to do anything to change them. I can just copy them into the document. And this chart is pretty terrible. Really, really ugly. A waste of space on the page. I didn't create it, so I'll just say that. The bar plot above shows what is I-rate? Let's look in the data dictionary. This is the short-term interest rate at the time of the call. It goes from 0.634 to 0.5 to 5. Shows the short-term interest rate. This graph is not very informative, but it was my assistant who created it. It shows. So let's instead of just looking at the graph, let's just look at a summary of interest rate. You can see below that I-rate goes 0.634 to 5.045. What is it that we're trying to do here? An actuary, right? And you're helping the marketing department. They've collected data on marketing phone calls, and they want to know what factors will be predictive of whether or not the person purchases the product, right? So this may be predictive of purchasing whether or not the customer purchases the product, but I would need to look at the purchase percentage as well to find out. What's the next graph? Create a bar chart for month. So the bar chart above shows the count of customers on the y-axis for each month of the year on the x-axis. Certain months, August, July, and May, have the highest call volume. This may be because customers are more active during these times, and so ABC Insurance could increase their staffing during these times to meet the demand and convert more customers. The next variable. What is EDU years? EDU years are just the years of education. So years of education for calling prospective customers. Yeah, so it's the number of years of education for the prospective customer. The graph above shows the number of years of education for the prospective on the x-axis and the number of customers on the y-axis. So most of ABC's customers are well educated, and it would be nice if we had labels for each of these bars, right? Except this graph doesn't give it to us. This graph would be easier to read if there were labels on the x-axis. But if you look back at the summary, easier thing to do is just do DF and then count DU years. There it is. So most customers have 16 years of education, which means that they completed 12 years of school and 4 years of college. So ABC Insurance may be able to market directly towards graduating college seniors because they are more likely to purchase than those who are still in school or do not have a bachelor's degree. So I also note that there are 468 missing values. It's not clear whether these are missing at random or not. There were 5 customers. There are 5 customers who had 1 year of education, which seems low. How is it possible that a person had only 1 year of school? This is a question that ABC should follow up with. Next, create a box plot for the age distribution for different jobs. So what are the variables age and job? Is there anything specific here? Job is just occupation category, and age is the age of the prospective customer from 17 to 98. So you can see here that the age differs by job, right? As you would expect. Those who are retired have a much higher age on average than, for instance, a student. So box plot above shows the customer's job category on the x-axis and their age distribution on the y-axis. These are box plots which show the median age as the center bar, the upper 75th percentile as the top bar, which is like right here, and the 25th percentiles as the lower bars down here. So ABC should customize their marketing strategies depending on the customer's age, and job. For example, customers who are retired are likely older and so may be more comfortable speaking on the phone than using online chat or email. Customers who are students may prefer text communication and be more responsive to social media advertising. Customers in the technician category tend to be between 25 and 45, and so they may not have a preference. And let's just do one more. Blue collar workers also tend to be 25 to 45 years old, as are, let's just see, blue collar entrepreneurs, housemaids, management. Just looking here, we're basically in the same age. You're like 25 to 50 is the same as self-employed services. And so these customers could all have a similar marketing strategy with regard to age. For instance, if younger people are less interested in retirement products than are older people. Candidates were expected to analyze and comment on a variety of charts, but some candidates did not comment on all of them, losing credit. This is one thing that I failed to do on my first attempt. I did not include all of the graphs that were needed. You can see here for the purchases by month, I included this graph here, but I didn't comment on it. And I failed to notice there was a pattern. So months that have more observations have lower purchase rates, and vice versa. So I've failed to notice that, which is maybe something that's easy to miss. And then I also included this table, although this isn't necessary. So I spent time that I could have used on other parts of the report on creating a table. And I also went into a lot of detail here about specific insights that they might benefit from. And this may have been a waste of time as well, because the question does not ask for it specifically. Task 2. Consider the education variable. Your assistant has created a new numeric variable, EDU years, from a categorical variable, using the following rules to map each category to a number. Basic 4-year goes to 4, basic 6-year goes to 6, and so forth. So this is basically a number that goes from 4 up to 16. Justify your choice of using a numeric variable instead of a categorical variable. Discuss the implications of that choice when running a generalized linear model compared to running a tree model. So first of all, let's look at the data dictionary. So in the data dictionary, we see EDU years. This is just the years of education, that integer from 1 to 16. Let's quickly look at the summary of the data. Here you can see that EDU years goes from 1 to 16, and there are some NA values. You can also look at the counts. You go to DF count EDU years. And it shows you that most people have 16 years, which is in a college education. Only a few people have 1 year. But the question is asking you to just consider as a numeric versus a factor type. Consider what happens if you have a numeric. If EDU years is numeric, then each is a factor, then it would have levels for each of these values. So it would have 1, 2, 3, 4, 5, 6, 7. It would have 7 levels, but one of them would be a base level. It would have values, 7 levels, which means that in a model, it would require 6 dummy values or indicator columns. If it's treated as numeric, then it only requires 1. So the advantage to using a numeric value is that it reduces the dimension of the data and helps to combat the curse of dimensionality, which says that as the number of predictors increases, the density of the feature space decreases, and so more observations are needed. The second part of the question is justify your choice of using a numeric variable instead of a categorical variable. Discuss the implications of that choice when running a GLM as compared to running a single tree. So consider what a tree would do. So if using a tree with a numeric variable where EDU years is equal to x1, it may look like this. We can't actually draw on this report, but just imagine that you could. You would say, here's x1, which is EDU years. This might be the first split, and it might ask, is x1 less than or equal to 12? Which would be, does the person have less than 12 years of education? If this is yes, it could ask, is x1 less than 8? And then based on this, it would ask another question, is x1 less than 3? And then, based on this, it might make a prediction and say, y is equal to 2, and if no, it would say y is equal to 3. And then these other branches could be like other variables. This could be, is x4 equal to 17, or is x5, or whatever. Maybe this this variable would just result in another split. This would be y is equal to 4. Right? So this would be if you're using a numeric variable. If you're using a factor, so this is numeric. Factor would be is x1 in the set 1, 2, 3, 4, up to 11. And then this next split would have to be is x1 less than or equal to 8. Is this in the list 1 to 8, right? And then if yes, it would, and then here it would do the same thing for x1 less than 3 and so forth. So it could functionally do the same things. It could fit the same model. It would be more complicated. And you could also have discontinuous possibilities. Like hypothetically, you could have a split where it says is x1 1 or 7 or 16, right? So this is non-linearity. Contrast this with a GLM, which can only do the following. So if x1 is numeric, then you basically just have, then you have EDU years, and then you have your linear predictor, z, and there are just some points here, and based on your coefficient, you fit some line that goes between these points. And it actually has to be a perfectly straight line, because there's just one coefficient. So you have a model that looks like z is your linear predictor, is equal to x times beta. It's equal to some beta 0 plus beta 1 times EDU years, which is just x1, plus some other things. If if a factor, the model is z is equal to, basically you have different coefficients for each value of the EDU years. So you have beta 1 plus this indicator, which is 1 if EDU years is equal to 1, and then you have another dummy variable, which is 1 only when EDU is equal to 2. You have another dummy variable, which is 1 if EDU is equal to 3, and so forth. So to type all of this out, I would say the decision tree, regardless of whether EDU years is a factor or numeric, the decision tree can fit non-linear splits, and the GLM cannot. This means that the tree is more flexible. If using a numeric variable, the GLM has only one coefficient for this predictor, which results in a simpler model. The factor would result in 6 coefficients. If using a tree, the complexity would be about the same regardless of the type. But you could say that using numeric makes the rules easier to interpret, because here this tree on the left is easier to read than a tree on the right, because EDU years has a high cardinality. That's just a fancy way of saying that it takes on a lot of different values, and so you could have lists here that are very long or complicated. Few candidates consider the difference in dimensionality from using a numeric variable. Often candidates did not distinguish between GLM and decision trees. Some candidates, when discussing decision trees, compared numeric and categorical and said that one was better than another without recognizing that, in this case, the decision tree could ultimately reproduce the original categories. The curse of dimensionality is a real problem in data analysis, although it isn't mentioned in too much detail on the SOA's modules, so it's understandable that some candidates would miss this detail. It's also worth noting that this rule about splitting wouldn't just apply to decision trees, but would also apply to GBMs or random forests. Task 3. Handle missing values. Check the missing value proportion for all variables. When you go ahead and run the code here, you'll see that it shows the percentage missing for each of the variables. EDU years is missing at about 5%, housing 2%, job 1%, loan 1%, and marital is less than 1%. So let's just copy this graph into the document, and we'll need to make some decisions regarding each of these variables. So I'm going to just create these different subheadings: EDU years, housing, job, loan, marital. Let's start with EDU years. First, let's look at the actual number of values. So you can do summary df, and it will tell you how many values are missing. So there are 468 values that are missing for EDU years. There are 468 values, which is about 5% of missing values for EDU years. This could be missing because the person never completed an education, because if you look at the data dictionary, EDU years is years of education from 1 to 16, so it's technically possible that someone would have no years of education. It's more likely that this is an error, though. So to fix this, I could either fill in the value with the average, or I could remove those people from the study entirely. So I could either remove these people from the data, or I could fill in the missing values using the average number of years. Let's look at the purchase percentage, because ultimately what we're trying to do is to help the marketing team to increase the percentage of customers who make a purchase. So I see that there's a difference here. So 54% of the people who purchase have missing values. I see that people who have a missing EDU years value, their purchase percentage is 54%, whereas people who have a valid record have a lower purchase percentage of 46%. So this implies that they are not missing at random, and so I don't want to remove them. I don't want to remove these records because there's some predictive power. If the value is missing, it means that they're more likely to purchase the product. And so I want to include that information. So for this reason, I choose to include the records by imputing the mean. And this code here says the following code can be used to handle missing values. Choose one of the 4 choices below to deal with the NAs. Choose for each variable that has NAs. Replace var name with the actual variable name. So here's remove column, remove rows, convert missing values to unknown, works only for factor variables, so it won't work for EDU years. Impute the mean. So let's impute the mean and say this is EDU years, and then I need to change this var name to EDU years, and this var name to EDU years, etc., etc. Run this, and then quickly look at the summary again and see EDU years has no missing values. Okay, what about housing? Housing has about 2.5%. Housing is missing in about 2.5% of cases. And consider the purchase percentage. See, housing here is 47% versus 46%. The difference in purchase percentage is just 47% versus 46%. And so I choose to remove these values. They are likely to be missing at random. And so removing them will not be omitting useful information for the marketing team regarding whether a customer purchases the product or not. So to remove values, you just go down to this code that says remove rows, and this is housing, and you just say df is equal to df where not is dot na housing. Okay. What about job? Job is missing in 1% of cases. In only 1% of cases, and consider the purchase percentage 41% versus 46%. There's a pattern in the missingness because the purchase percent for those with missing job field is 41% versus 46% for those who have valid records. So it could be that people without a job are at a higher risk, higher financial risk, and thus are more likely to purchase insurance, and that these people may have. So it could be that people who have had their data incorrectly recorded so that their job is unlisted are at a higher risk, higher financial risk, and thus more likely to purchase insurance than those people who have their data recorded correctly. For this reason, I will fill in the values using other. So let's look at the job. It's occupation category. Oh, it's a factor with 11 levels. So let's quickly look at df and then count job. And these are all the values. Unemployed, NA. So there are 90 values which are NA. I don't see that there's an other field, so I'm just going to say I'll create a new field that's called missing. And the way to do that is just to do this. Convert missing values to unknown. Works only for factor variables. So the variable here is going to be job, and the level is going to be, and then if you look again at the count of job, you should see that there are 90 cases. That's not right. Let's do something else. So let's say is.na job is equal to missing. It's still not working. So let's say df equal to df and mutate job equals if else is.na job yes is equal to missing, no is equal to job. Now let's look at the count. Okay, and there's the values of missing. Let's make this a lowercase m. Actually, it doesn't matter. Okay, now we just have left the loan and marital variables. So we see that loan has about 1% missing values. And let's just check what those values are. So I'll just do df and then count loan. And I see these are just yes or no. Let's just look again. Oh, it says that loan has no missing values, which is excellent. So we can just skip this one. So actually, let's be careful here. Loan had no missing values after I removed the records which were missing from job, actually from housing. So once I removed the missing values from housing, there were no missing records from loan. Let's just try that again. So if we go back to the original data and then you look at the summary, you'll see that, there are still no missing values for loan. Oh no, so there are. So there are 119 values which are missing. But this doesn't tell you if the values are missing. I believe this is because this is a character. So if you convert this to a factor, df mutate if is character as factor, then summary. Yes, okay, so here you can see the NA values for loan. There are 119 values which are NA. But after we removed values where housing was not missing, right here, and we go back and run this, we'll see that there are no missing values for loan. So we can just say that. So loan had no missing values after I removed the records which were missing from job. And so you can also look at the percentage of the purchase percentage for missing versus not missing. So for missing, it's 46%. For not missing, it's also 46%. So that means that we don't expect that if it's missing, that info will be predictive. The purchase percentage was 46% for both missing and non-missing cases. And so this is safe to remove without losing predictive. Okay, finally, marital. So marital here had only about a few cases which were missing, and here again it's showing as a character. So let's try a count, and there are 23 records which are missing. 23 records after removing the other variables. So after removing the missing cases, which from housing, loan, and housing, there were 23 remaining cases which had a missing value for marital. And then consider the purchase percentage. 52% versus 46%. That's a significant difference. There was a significant difference in the purchase percentage, because this was 52% for where marital was missing, and only 46% when it was not missing. So for here, but because there are only 23 cases, I felt that it was safe to remove these values, because you're looking at 20,000 out of almost 10,000 records. So even if they were significant, there would not be enough sample size to give them credibility in a model. So let's just remove them here, and there it is. And so that covers all of, and that now as a check, you should go sum is.na df. And this tells you, that there are actually still 540 missing values. So we've missed something here. Let's look at a summary again. It's not right. Let's look at, we should be able to rerun this, and it would tell us the percent of missing, right? If we've done our work correctly, these should all be nans. Okay, so there's still some missing values in job and EDU years. Let's look at missing data. So for job, marital, and housing, and loan, and EDU years, there's still some missing values. So let's go back and just rerun everything. What probably happened is that because I went back and reran some of the data, it undid my prior, which is why it's always important to have checks for the steps that you do. And this doesn't make sense. This is saying that there's still NA values for marital, but I've just removed it right here. So let's go and use this trick to convert back to a factor. Okay, so there's nothing here missing in marital. Oh, their name. So what happened here is because I accidentally copied the code incorrectly and then ran it, it added this new column called var name. So to remove it, I can just go df var name is null. Now if I do sum is NA, now there's 0. Okay, so that was the whole problem. 1, I had run the code in incorrect order, and 2, I had added this extra var name column. For those of you who are using the dplyr syntax, here's how you do all of this in one step. So you just do df. I'll put this in a new block and I won't run it. I'll use eval equals false, so it won't run this block. But you just do df is equal to df, and then filter, because you want to remove rows. And then first you want to impute the mean for EDU years. All right, so do that. You want to use mutate EDU years is equal to if else is.na EDU years. And if that's true, then you want to use mean df EDU years. And if it's false, just keep using the same EDU years. And then you want to filter out all of the records that are missing for housing. So you want not is.na of housing, and you want not is.na marital. And then finally for job, we move this to a new category called missing. So you want to add another mutate argument. So job equals if else is na job, yes is equal to missing, no is equal to job. And that's how you would do it using dplyr. One of the advantages to using this method is that when you run this, it will do it all at once, and so you won't have that error where you run it in sections, get an incorrect answer that way. Task 4, 3 points. Investigate correlations. Create a correlation coefficient matrix for all the numeric variables in the dataset. Among these pairwise correlations, determine which correlations concern you in building a GLM and tree models. The response may differ by model. State a method other than principal component analysis that can be used to handle the correlated variables. Do not implement this method. Let's look at the correlation matrix. This is showing each of the numeric variables in our data set. So to make this a little bit easier to read, let's just put this into Excel. On the real exam, you shouldn't do this. On the real exam, you should just use the result in RStudio. But for illustration purposes, it may be helpful to see. So I compare the correlations of the linear variables below. So the two strongest correlations. So first of all, what is a correlation? A correlation is the tendency of one variable to increase as another variable increases and to decrease when that variable decreases. Let's be more correct. Two variables are correlated when there is a tendency of one variable to increase as the other variable increases and to decrease when that variable decreases. So I see that EDU years and age have a negative correlation, and these other values are weaker. Except for interest rate and CPI have a very high correlation of 0.59. And then also employment and CPI also have a high correlation, 0.38. And what is the question asking? Okay, create the matrix. Among these pairwise correlations, determine which correlations concern you, and building the GLM and tree models. So what are the assumptions of a GLM? One of the assumptions is that the predictor variables are not correlated. These correlations between I-rate and employment may cause problems when fitting the model. Decision trees, on the other hand, handle correlations well and would not be impacted. So GLMs perform poorly because there are separate coefficients for each of the correlated variables which have an offsetting impact. This results in an unstable model which can have its coefficients change drastically depending on the training split. The p-values for the correlated variables will likely be large. Trees are not impacted strongly by this because only one of the variables will be selected at each split. In other words, the feature selection attribute of trees will only choose one of the correlated variables at a time. And then the final part, state a method other than principal component analysis that can be used to handle the correlated variables. Do not implement this method. So there are at least 3 methods that could be used. So one of them would be to remove one of the correlated variables. Another would be use stepwise selection, such as step AIC or step BIC, and another would be to use lasso regression, which would remove variables. If you removed one of the correlated variables and then left the others, there would no longer be the issue of having counteracting coefficients and an unstable model. If you used step AIC or BIC, you could remove a subset of the correlated variables automatically. That's because once one variable is included in the model, adding another correlated variable would not lead to improvement in the AIC or BIC, and so this model variation would not be used. Finally, use lasso regression. It would remove the variables which are not adding predictive value. So this would remove variables which do not decrease the test error, which would be root mean squared error, probably based on the cross validation. So you only need to choose one of these answers, and you could just choose any of these, and as long as you explain it well, you should get full credit. Which correlations were concerning can be a matter of judgment, though the 94% correlation between I-rate and employment clearly needed to be discussed. I made a mistake here. When I was writing the report, I actually wrote 0.38 instead of 0.98. This definitely would have cost me some points on the question because they specifically say that the correlation of 0.98 is mentioned. It was common to not relate the correlations to specific modeling techniques, which was to look at the decision tree versus the GLM. And some candidates mentioned clustering as an alternate technique, but the type of clustering was important, as some clustering approaches do not easily accommodate new observations for prediction. I think what they're talking, so for k-means, you'd have a number of cluster centers, but k-means doesn't work if you have categorical data, right? K-means is only for numeric data. Hierarchical clustering could use a mix of both data types, but if there are new categories in the data, it would not accommodate prediction, or new combinations of categories. So yeah, I think clustering is actually another alternative approach that could be used. Here I said you could deal with correlation by removing a correlated variable, using stepwise selection, using lasso regression. Another alternative would be to use clustering to create a new feature which captures the pattern. So you have customers who had similar cluster characteristics for correlated variables would be grouped together. For instance, I could use k-means on the economic. Task 5. Conduct a principal component analysis. Your assistant suggested PCA might be a good way to handle correlated variables. Perform a PCA on the following variables: CPI, CCI, I rate, and employment. First of all, what are these variables? Let's look at the data dictionary. CPI is the Consumer Price Index. CCI is the Consumer Confidence Index. And I rate is the short-term interest rate. And employment is the number of employees of ABC Insurance at the time of the call. So you're looking to create a principal component analysis, which simplifies these variables down into a subset of principal components. So let's look at the R code that they provide. On task 5, I see that they say principal component analysis of the 4 variables below. The variables are standardized. Then the components are calculated. So I just go ahead and run this code chunk, and I see some of the output here. So first of all, let's just explain what PCA is. And this answer will basically be the same for any type of PCA question that you have. So just say something like principal component analysis, PCA, is a dimensionality reduction method which takes in the original variables and simplifies them. PCA is a good way to handle the economic variables, I rate, CPI, and employment, because I saw from earlier that these are correlated. And I like to just describe what the algorithm is doing. So whatever model I'm using, if I'm using a GBM or a decision tree or PCA, so PCA begins with the original variables and then applies scaling by subtracting the mean and dividing by the standard deviation. You can look at the cheat sheets to see that you begin with these original variables x's and then you translate into principal components, and each principal component is a linear combination of the original variables, and the weights that are used are called the loadings or the rotations. Variables are scaled first, and when columns are completely uncorrelated, the principal components are the original x's. So then it creates linear combinations which are uncorrelated, orthogonal. Okay, what is the next part? Create a biplot of the first 2 principal components and explain the loadings of the first 2. So let's go to the code here, and I need the loading factors. Those are also called the rotations. Right here it says rotation, and I also need the biplot. You just copy the biplot. Shows the projection of the original variables onto the first 2 principal components. So I notice that these variables are grouped together, CPI, employment, and I rate, because they're correlated. And I rate are grouped together because they are correlated. If you look back at the correlation matrix, you can see like CPI and I rate have a correlation of 0.59. I rate and employment have a correlation of 0.9 correlated, and then CPI is almost perpendicular. This is about a 90-degree angle, and if you look at the correlation between like I rate and CCI, for instance, there's CCI and there's I rate, and the correlation is about almost 0.06, which makes sense because the correlation between CCI and I rate 0.06. So to interpret the principal components, I look at the loadings. So the recipe for the first principal component is, and then I take minus 0.47 times CPI plus 0.06 times CCI minus 0.64 times I rate minus 0.6 times employment. The recipe for the second is 0.21 times CPI minus 0.96 times CCI minus 0.17 times I rate and minus 0.08 times employment. And you could interpret this first one as an economic index, where it increases as the CPI, the consumer price index, or the interest rate, or the employment decreases. So is below. This can be interpreted as an economic indicator, which is high when the economy is in a recession, when interest rates, employment, and prices are lower, and low when the economy is growing. And the recipe for the second is below. This gives more weight to CCI. So this is the loading for CCI is 0.96. The loading for CCI in the first is only 0.06. This PC has a larger rotation on CCI, 0.96, as compared to the first PC. Okay, what's the next part of the question? Explain why it's appropriate not to consider age and EDU years for the PCA. Well, age and EDU years, let's look in the correlation matrix. Age and CPI, CCI, these are all really small correlations. Same with EDU years. And that makes sense, right? Because why would someone's age be related to the current state of the economy? So it doesn't make sense to add age and or employment or EDU years to this PCA because these are unrelated to the state of the economy and have very low correlations. You might have heard the saying, correlation does not imply causation before, which is true. If two things do have a correlation, it doesn't mean that they're related to each other. If two things are not correlated, though, it doesn't mean that they're not related at all, because you can have relationships that are nonlinear. But for the purpose of PCA, which can only look at linear relationships, it would be useless to add them. So this would only make the PCA more difficult to interpret, and the variables would not explain any of the variation in I rate, CPI, CCI, and employment. So only the first principal component will be used. Run the code to attach it to the data frame. So let's look here below, and we see it says red is equal to a new data frame, which takes in these columns, and then it creates a new column in our original data called PC1, which is just the PC1 part. And then if you look at the head of the data, and go over to the end and see there's PC1 that's been added to your data frame. The information that you get from the biplot is actually the same that you get from the values of these rotations. Now remember that for any vector, you have two components, a direction and a magnitude. The direction tells you how far to rotate. Call this theta. This is the rotation of the loading. And then you have the magnitude. The magnitude tells you how far to travel in that direction. So you might have another vector that looks like this, that's longer. You would say that this has a greater magnitude. And in this case, this would also have a greater rotation. So look at this graph, for instance. On the x-axis, you see the first principal component, and on the y-axis, you see the second. So the rotations here tell you whether or not increasing this variable will increase or decrease that principal component. Look at I rate, for instance. Clearly, if you travel along the value of I rate, right? You travel along this vector. Just imagine that you're an ant walking along this line. So your interest rate would be going up, and that would be decreasing PC1. And so look at the sign of I rate onto PC1. It's negative 0.64. Conversely, look at the sign. Imagine that you were right here and you were walking this way. So you would not really be increasing PC1 by very much, right? So if you're walking along the CCI vector, you would be only increasing PC1 by 0.08. 6. So that's how you can interpret the rotations just from looking at the biplot. It's also worth mentioning that this is just showing the first two principal components. If you want to, you could also look at the second and third principal components using this code here. This is going above and beyond the exam solution because they don't expect you to make changes like this. If you did this though, you could see PC2 versus PC3. And let's see if we can deduce the signs here without looking at the above table. The fact that CCI is pointing to the left, as you increase CCI, you decrease PC2. The fact that CPI increases as PC3 increases means that the sign of CPI is going to be positive on the third principal component. Let's go back and check. From the third principal component, you can see that CPI has a positive sign of 0.83, and that agrees with the graph. Candidates generally printed the biplot, but often did not indicate how to read the plot when explaining the loadings. So in this case, you need to explain the graph as well as the loadings. So in general, whenever they ask you to include a graph, it needs to be explained. On our video, I think we spent a lot of time explaining the loadings, and we actually included the loadings specifically. However, the SOA solution was a lot faster. They didn't spend their time doing so, and so this is one area where you could save yourself time. Our solution, though, was also intending to give you more details about PCA because you might have a slightly different question. Your question might ask you to interpret the rotations. But on the real exam, it's a good idea to only do what they're asking you to do. Task 6. Create a generalized linear model. This is only worth 5 points, which is low because most of the time these modeling questions are given more weight. So I noticed that there are a lot of bullet points here, and it's only 5 points. So I want to be careful to only do what they tell me to do. Fit a GLM using a binomial distribution in a logit link function on the training dataset. Use age as the only explanatory variable for purchase. So first I have to run the code that splits the training and the test data. And this also compares the mean of the purchase percentage between the two datasets. And I see that this is about 47.46 in each. So first I will just comment and say that. First, I split the data into training, which is 70%, because here it says p is equal to 0.7, and test 30%. I will train the model on the training data and evaluate the performance on the test data. And I checked that the purchase percentage was about 46% in each data set. And now construct a GLM using age as the only independent variable. So let's go ahead and do that. And you might be wondering why you only use age as the predictor. And this is actually a common technique in machine learning. If you need to fit a very complex data pipeline or a sophisticated model, you can often encounter errors. You might have problems with the data or problems with your algorithm, and it can be challenging to tell if you're making progress or not in your modeling. And so a good strategy is to first fit a baseline model, which uses only 1 or 2 variables, and then in your subsequent modeling analysis, you can compare your performance against this baseline to see if what you're doing is improving the result or not. So this case is just a single predictor. So we'll be able to compare our future models against this simple baseline. And this shows the ROC curves and the AIC on both the training and the test data sets. However, I really don't care about the result on the training data. I am only interested in the result on the test data. And now, because I remember that this question is only 5 points, I just want to see what they ask me to do. Run the summary function in the first and provide the output. So here's the output, okay? And I will just say, I fit a GLM that used only age as the predictor. Next part, fit a second GLM using a binomial distribution with a logit link function on the training dataset. Use all the explanatory variables. including the first principal component, and excluding the 4 original variables used in the PCA. So that's what this does. Construct a GLM using the full set of independent variables and the first PC. And then I'll just copy the results into the document. Then I fit a second GLM using a binomial family and a logit link that included all of the variables except for the economic variables, which used the principal component instead. And I actually see that there's an error here. See how the R console copied way too much information, which does happen. So I just press Control Z to undo it. And just have to be careful when you copy these results that you don't get too much of the text. It's really a glitch in RStudio. Okay, so there's the result below. And I also want to get the AIC value. And I can see that this AUC curve is much steeper than the earlier one, which is good because I would expect it to be, because it's using all of the predictors. And then I need the actual AUC value. Okay, and they said fit a second GLM, use all the explanatory variables, including the first PC, and excluding the 4 original variables. And then run the summary function of the second GLM and provide the output. Now, the marketing department thought age would be a significant feature in determining whether a prospective customer would make the purchase. The significance of age is different in the 2 GLMs. Explain why this is the case. This is really the heart of the question. So let's go and look. In the first model, this is the coefficient, right? 0.007, and the p-value is very small, which indicates that that is significant. In the second model, the coefficient is still positive. However, the p-value is quite large, indicating that that variable age is not significant. Why is that the case? First, let's just state what we observe. First model has a positive sign on age, which means that the purchase percentage increases as age increases. The p-value is small, indicating that it is adding predictive value to the model. The second GLM, which uses all of the other variables, also has a positive sign on age. The p-value here, however, is large, 0.38, which means that once all of the other variables are taken into consideration, age is no longer a predictor of whether or not a person purchases insurance. And that makes sense intuitively, because if I tell you a person's job, their marital status, educational years, their housing, the type of loan, the month and day of the year that I call them, and the state of the economy at the time, you don't need to know how old they are in order to tell me if they're likely to purchase or not. However, if you tell me nothing about a person except for their age, then based on their age, I'll be able to at least make an educated guess as to how they'll purchase. I'll at least be able to say, okay, younger people are less likely to purchase than older people. But once you give me all of this other info, I can already tell you if they'll purchase or not. And so what was the question asking for? Explain why this is the case. So you could also type that out. So this makes sense because once I know a person's housing status, their job, their occupation, their loan history, all of the other variables, the month, educational status, month, educational history, the month of the year, educational history, along with other info, I can already predict whether they will purchase or not without knowing their age. On this question, I failed to comment on the AUC being very low for the age-only model. So I included the AUC curve as follows because that's what the question asked me to do. However, I didn't say that the AUC of 0.52 was low, which it is, because if you were just randomly guessing, you'd get an AUC of 0.5. In my defense, however, the project statement doesn't specifically tell you to look at the AUC. They say fit a GLM and run the summary function and provide the output in your report. But they don't tell you to look at the AUC or the performance. Instead, what they say is the significance is different in the two GLMs. Explain why this is the case. So this was really up to me to make that observation. So be careful here to think for yourself. If they ask you to make an explanation, don't rely too heavily on following the bullet points. Task 7. Select features using stepwise selection. This is worth 8 points. Your assistant has suggested that adding the square of age as a feature may improve the model. Explain, without running any models, why this is or is not a reasonable suggestion. Regardless of your conclusion, add the square of age to subsequent models when asked to. So when does it make sense to add the square of a variable to the model? Look at the exploratory plots of the age variable. And so this shows here the purchase percentage on the y-axis by age. And so you can see that this trend starts out high, and then the purchase percentage decreases and then begins to increase. And so this is a non-linear trend. And GLMs by themselves only capture linear trends. This means that there has to be a straight line in the impact that a variable has on the response. So you could deal with this in a few different ways. One way would be with a decision tree. A decision tree would fit separate nodes for each for different values of age, and it would predict a different purchase percentage. So it would say for people between the age of 25 and 40, the purchase percentage is predicted at 0.4. For people over the age of 40, this increases up to 80%, right? The other way is with a polynomial term. As you probably remember, the equation for a polynomial involves something like ax plus bx squared plus c, right? So you need a second order term in order to get the polynomial. And so when you add the square of age, it allows you to fit that polynomial on top of your model. Going back to the basic algebra, you can see the difference that adding this square term makes. On the left here is the equation of a line. You are already familiar with the form y is equal to mx plus b, where m is the slope of the line and b is the intercept term. So the linear predictor is just z is equal to beta 0 plus beta 1 times age, which you can think of as a linear term. However, when you add the age squared, you get something of the form beta 0 plus beta 1 times age plus beta 2 times age squared. You can think of this as the equation for a polynomial, ax plus bx squared plus c. Recall from algebra class that polynomial that you see here has starts out positive, it decreases, and then increases again. And this is in agreement with the graph that you saw earlier. So to summarize, in the data exploration task, I noticed that the purchase percentage by age starts out high, decreases when the person is between 30 to 45, and then increases as they turn 65. Using just age by itself in a GLM would fail to capture this pattern. If a single variable is used, then there is only one coefficient on that variable, and so the impact can only be positive or negative. If this were a decision tree, this would not be a problem because separate nodes could predict different purchase percentages. By adding in the square of age, I allow for the linear predictor to capture parabolic trends, which have a decreasing and increasing pattern that I saw in the graph. This would likely improve the model. Some of the features may lack predictive power and lead to overfitting. Best subset selection fits separate GLMs for each possible combination of features and selects the best combination. Discuss the advantages and disadvantages of forward or backward selection compared to best subsets. So this is really just asking for your knowledge of the definition. So best subset selection is when you consider all possible models. This includes the model of just age and EDU years, age and EDU years and marital, age and EDU years in marital and CPI, and so forth. This search through all possible combinations, subset of variables, which has the best performance. So one advantage of using stepwise forward or backward selection is that fewer nodes are considered, which reduces the likelihood of overfitting. Because so many models are considered in a best subset selection, it is likely that some combination randomly has a good model score, despite the fact that the relation may not reflect reality. So using stepwise selection looks at fewer models, and so it's less likely to overfit, and the model that it finds tends to perform better on new data. One advantage to using stepwise forward or backward selection is that fewer models are considered, so that it is possible that a better performing model exists. Forward selection starts with no variables and only adds the variables which improve the score. Backward selection starts with all the variables and removes them until the best model is found. The choice of using either forward or backward selection is somewhat arbitrary and is left up to the actuary running the model. Using backward selection will result in a simpler model that is easier for the marketing department to understand. The resulting model can be explained in a spreadsheet using only the person's age, EDU years, the month, weekday, and PC score. This removed job, marital, housing, and phone variables. From a cost perspective, using fewer variables is more efficient because data needs to be purchased, collected from customers, and stored in databases. So in the R code you saw this step AIC function, and if you just run direction is equal to backward and k is equal to 2, then this is the result. So you can see that it's using age squared, EDU years, month, weekday, and PCI. So the variables that it removed are the job, marital, housing, loan, and phone variable. And then you just copy this formula like so down into the next GLM and then run this. Now you can see that almost all of the p-values are less than 0.001, which is a great sign. It means that it's removed variables which are not predicted. There are two weekdays, Thursday and Tuesday, which are not predictive. The reason why these were not removed is because in step AIC, R only removes the all weekdays at once. So because weekday was included as a factor variable, it could either keep in all of the weekdays, Sunday through Monday, or it could remove all of them. And because some of the weekdays are predictive, like Monday, for instance, it also keeps in Tuesday and Thursday, even though there may not be any difference between them. So the variables remaining all have p-values that are small, except for certain months and weekdays. The age squared predictor is adding predictive value, as can be seen by the small p-value, which you can see right here. The signs of the coefficients tell us if that variable increases or decreases the purchase percentage. I noticed that the signs of age and age squared are opposite of each other, which agrees with the trend that we saw where the purchase percentage decreased and then increased. So see here, you can see the age coefficient is a negative, but the age squared coefficient is positive. Task 8, 12 points. Evaluate the model from task 7 on both the train and test data. As part of your evaluation, output the AUC for both sets of data. I see that the AUC of the model looks good. This is 0.7836 on the training data and 0.774 on the test data. Explain what AUC near 0, 0.5, and 1, and almost 1 indicates. First of all, what is AUC? You can remember this simple interpretation. AUC is a probability. It's the expected proportion of positives that are ranked before a uniformly drawn negative. Or this is the probability that a randomly chosen purchaser is given a higher predicted value than a randomly chosen non-purchaser. Let's go ahead and write that into the report. I would just say AUC can be interpreted as a probability. This is the probability a randomly chosen purchaser is ranked higher than a randomly chosen non-purchaser in AUC. So then let's consider the different scenarios. An AUC of 0. How is this possible? First of all, what is AUC? If you were to look at a graph like this, where the predicted probability was on the x-axis and the number of customers was on the y-axis, you would see two groups. Those who did not purchase, who generally had a lower predicted probability, and those who did purchase, who would generally have a higher predicted probability. If the model is doing a good job, these two groups will be far apart. Then you create a cutoff value, which is between 0 and 1. And if a person is above this cutoff value, you say that they're predicted to have purchased. And if they're below the cutoff value, you say that they are not predicted to have purchased. So if you want to change your false positives or false negatives, then you change this cutoff. So there are three scenarios here for AUC. The first one is that AUC is equal to 1. This is where the classes are perfectly separated, which means that there's no overlap between the two. In other words, every person is given a perfect prediction. The ROC graph, which shows 1 minus the specificity on the x-axis and the sensitivity on the y-axis, would look like this 90-degree right angle. You can create this in R for yourself if you are interested. The way to do this is quite simple. You simply set your test probability, your test predictions equal to the actual values of the label, and then you just run the graph. You can create this for yourself quite easily. You just set your predicted probabilities equal to the actual labels in the data. And then you can see here that this graph is a perfect right angle and the AUC is equal to 1. Another possibility is that your AUC is equal to 0.5. In this case, your model is doing no better than just randomly guessing. So your classes are overlapped and the ROC curve is a horizontal line. The area under this curve then is 1/2 of 1 or 0.5. You can also create this type of graph in R as follows. You simply randomly choose the customers as 0 or 1 in the same proportion to the actual data. I do this by taking permutation of the test set purchase column. In other words, I just randomly shuffle the column of purchases as 0 or 1. And so that just like there's a 47% chance overall that each person purchases, this shuffled permutation still has a 47% purchase rate overall. And then when you run this, you'll see that the AUC is basically 0.5 and the AUC value comes out to about 0.5. Another possibility, which is interesting, is that the AUC is near 0. This indicates that something is seriously wrong. There are two ways that this could happen. The first is if you severely overfit your data so that your training AUC would be high, but your test AUC would be very low. The second way is if there's an error in your AUC calculation and there's something wrong with the formula. So go ahead and summarize this in your document. And again, there are a number of different ways of answering these questions. There's no single right answer. Something that I would say would be, an AUC of 1 would be a perfect model. The ROC curve would be in the upper left-hand corner, showing that the sensitivity is 1 and the specificity is 1 for all values of the cutoff. The AUC of 0.5 would be a random guessing model. That means that each customer would be given a 47% chance of being a 1 and 0 otherwise. An AUC of less than 0.5 indicates that something is wrong. Either the model is overfitting so that the training AUC is greater than 0.5 but less than 0.5 in the test data, or that there is an error in this calculation. Compare the selected features as they relate to the data analysis performed in earlier tasks. Comment on how any results are different than the expected data exploration in task 2 and the second GLM in task 6. This question asks that I go back and review a lot of my earlier work. So let's do that. I want to split the windows up into 2 screens so that I can look back at my earlier work. To do this, I go up to View and then Split, and then I'll scroll up here to the data manipulation tasks. For the month variable, I noticed that some months had fewer observations than others. And if you look at the results of this model, I can see that the p-values for August, for instance, are quite large, as well as December. And I noticed that for December there are not many observations. In task 1, I noticed that there were some months, December and March, which had few patients. These months have larger p-values because there is less confidence in the coefficient estimates. And then for the EDU years variable, I noticed that there are some years that have no records. I noticed that there were some EDU years which had no patients in them. If I look at EDU years, I can see that it's still significant though, because the p-value is very small, right? This is okay because it is a numeric variable and instead of a factor, and the p-value is small. I noticed some combinations between age and job. For the age variable, I found that I needed to add a squared term in order to make it more predictive. And I can see here again that age and age squared are both significant predictors. They have opposite coefficients. And remember that when I fit the model that just had age in it, that the coefficient was not significant. See here? See, this model is just using age and it's not predictive. However, when I added in age squared, suddenly it became predictive. The age variable by itself was not predictive, but when I added age squared, this was able to account for the nonlinear trend, and so both were predictive. The coefficients have opposite signs indicating the change in direction. And then I did the missing value analysis, and then I also looked at the correlations, but that was in later tasks. This is just asking you to compare the selected features as they relate to the data analysis performed in earlier tasks. Comment on how any results are different than expected from data exploration task 2 in the second GLM in task 6. And then interpret the coefficients from model 7 in a manner that will provide useful information to the marketing department. This part is worth 5 points. First of all, let's get rid of this split windows. I go up to view and then remove split. And then I want to move these coefficients into a nice table. And so I will move them into an Excel table. Data, text to columns, delimited, space delimited. Let's get rid of these unnecessary columns. And then I want to take the exponent of this term. And then I'll just round these numbers so that they're easier to read. So how do you interpret these? Any GLM, you start with a base class, and then you multiply the product of the exponents together. So in this case, what are the base classes? For the factor variables, it's actually not immediately obvious. The SOA's answer doesn't tell you how they find the base month. There are two ways that you could do this. You can just type in levels into the console. So you go to levels and then data train month. And this will actually tell you nothing, because you have to convert this to a factor first. And then you'll see that the base month, the base level, the first level is April. You can do the same thing for this weekday. See, because all of these coefficients are relative to the intercept term, and the intercept term is taking into account the base level, and this is Friday. So the logistic regression can be interpreted so that a product of numbers creates a log odds of a customer purchasing. So to begin, it starts with the reference level. This is the month April, weekday of Friday. Let's see other factor variables. Just month and weekday. And then you can think of the interpretation. So each of these is going to increase or decrease the linear predictor. So you can see that age has an effect of, so the log odds increase or decrease by a factor 0.93 for each year of age. So we start, this is right. So the log odds decrease by a factor of 0.93 for each year of age. So if a person is age 20, then multiply by 0.93, 20 to the 20th. The impact that age has is not linear, and so this age squared term accounts for this. And I'll increase the decimal points here so that it's easier to read. And so this shows that you also multiply by 1.001 times to the n, where n is the person's age squared. And so the log odds increase as the person's education increases, multiply by 1.029 to the n, where n is the person's years of education. And finally, let's just look at one of the categorical variables. So for the month of August, log odds are 22.4% higher for the month of August as compared to the reference month of April. You could do the same thing for a weekday. So the log odds are, in this case, 23.6% lower on Mondays as compared to Fridays. And then the principal component. So remember that this is another numeric variable. So the log odds increase by a factor of 1.951 to the n, where n is the value of the principal component score. So remember, this is the economic score, which increases as the interest rates, employment, and confidence index increase. And then you want to put this into a nicer format so that you can read it in your document. So I'll just hide these two middle columns. Actually, no, I'll just leave them. Well, let's see. Who is the audience going to be for this question? It says, interpret the coefficients in a manner that will provide useful information to the marketing department. So really clean up the language and try to remove anything that's too complicated. So I see that I'm using the word log odds, so I'll need to explain what log odds means. And let's make this first interpretation easier. So the log odds decrease by a factor of 0.93 for each year of age. For example, if a person is age 20, then multiply by 0.93 20 times. Or just multiply by 0.93 to the 20. And I'll say, let's just combine age and age squared together into a single table. So let's just make a new table. Let's just use these variables, age and age squared, and then month, August, years of education, and then weekday, Monday, and then principal component. And then I'll just summarize this age and age squared. So as log odds decrease by a factor of 0.93 for each year of age, and increases by a factor of 1.001 for each value age squared. And to summarize this, I'll say there's a decreasing. The purchase log odds are highest for younger people and older people. And then I'll just use the same interpretations for education and month August, as well as weekday Monday and the principal component. And I'll just clean this formatting up, make the table easier to read, improve the spacing, and add wrap text. And then this will be the variable. This will be the interpretation. Finally, let's add some borders to this table, and then copy as picture as shown when printed. So the logistic regression can be interpreted so that the product of numbers creates a log odds of a customer purchasing. So this is the probability that a customer purchases divided by the probability that they do not purchase. To begin, it starts with the reference levels. This is the month of April and the weekday of Friday. I can actually remove this. Oh no, I'll just leave this. So the marketing department can use this table to help them better understand their customers. Let's just go back and make sure that we answered everything. Interpret the coefficients in a manner that will provide useful info to the marketing department. This part alone was worth 5 points, so it's worth investing in. Task 9 points. Investigate a shrinkage model. ElasticNet could also be used for feature selection. Explain how ElasticNet performs feature selection. If you look at the cheat sheets, you can see the differences between the ElasticNet, Ridge, and Lasso models. So all of these models use what's called a penalty term on the log likelihood. So the objective function, which the model is trying to minimize, is minus the log likelihood divided by the number of observations plus some other term. In the case of the lasso, it's optimizing the negative log likelihood plus the sum of the absolute values of the coefficients. This has the impact of removing variables. The ridge model optimizes for the negative log likelihood plus the sum of the squares of the coefficients. Finally, the ElasticNet optimizes for the negative log likelihood plus a weighted average of this first term and the second term, where the weight is controlled by the alpha parameter. You don't need to memorize all of this for the exam because in the R documentation you can find these formulas. If you just load the glmnet library and then type in !glmnet, you can find this info. So here's the documentation, and here it says that it fits a generalized linear model, penalized maximum likelihood estimation. And here's the info about the alpha parameter, which controls the weighted average of the sum of the squares of the coefficients and the sum of the absolute values. And then if you scroll down here, it gives you details about the penalty term. So this first bullet, explain how ElasticNet performs feature selection. It's just asking for a statistical explanation. So ElasticNet performs feature selection by maximizing an objective function. This includes the negative log likelihood. So guys, what I'm really just doing is I'm just looking at this table. So what I'm really just doing here is I'm just taking this formula here and I'm rewriting it in words. There's really nothing else that I need to do. So ElasticNet performs feature selection by maximizing an objective function. This includes the negative log likelihood as well as a second term. In the case of the lasso, this is the sum of the absolute value coefficients, which has the effect of removing variables by setting their coefficients to 0. In the case of ridge, this is the sum of the squares of the coefficients and has the effect of making the coefficients smaller. There's also a third case, which is a combination of the lasso and ridge, known as ElasticNet, which uses a weighted average of the first and second penalty terms. This is controlled by the alpha parameter. When alpha is equal to 1, then the second term goes to 0. So you just have the absolute value, which means that you have ridge. When alpha is equal to 0, the model is the ridge. Use ElasticNet with alpha equal to 0.5 to create a regularized regression. Use the same variables as the second GLM in task 6, plus the square of age. Let's look at the code that they provide. Here I can see that they add the square of age. They do this for training and test data sets. I just go ahead and run this code, and then I see the following outputs. This graph shows the shrinkage parameter against the misclassification error. Note that this is actually the log of lambda. But as you increase lambda, you also increase the log of lambda. So when you have a higher shrinkage rate, the error rate increases. So you want to choose the lambda that has a low error rate. But you don't want to choose lambda that's too small, because what will happen is that this will not shrink the model at all. In other words, it will just, so if you set lambda equal to 0, for instance, then you are using no penalty term and you're just using the original GLM. And that defeats the purpose of shrinkage. So all that this says is use ElasticNet. It doesn't say that I need to create the graph or anything. So that's all that I need to do. And then I need to use the cross-validation results to run the final ElasticNet regression model. So here, this uses CV GLMNet, so cross-validation GLMNet, to find the best value of lambda, right? And then this will use lambda min. So lambda min right here, if you wanted to see what this was, it's just a number. It's 0.002, 0002, etc. So then you get the coefficients here. So notice that all of these coefficients are non-zero, meaning that the original variables are all included. So explain why using alpha equals 0 is not appropriate if the goal is feature selection. Well, when you have alpha equal to 0, what do you have? Do you have the ridge regression, or do you have the lasso? If you want to remember this, just type glmnet, $glmnet into the console. This brings up the documentation. And if you look at alpha, you can see alpha equals 1 is the lasso penalty. alpha equals 0 is the ridge penalty. So if our goal is to remove variables, then we need to set alpha equal to 1. If we want to shrink the size of the coefficients, then we should choose an alpha greater than 0. Setting alpha equal 0 is the ridge model, which does not remove any features. Evaluate this model on both the train and test sets. As part of your evaluation, output the AUC for both sets of data. So here are the ROC curves, and the AUC values are 0.784 and 0.7729. So these are better than the prior model. The AUC is 0.784 on the training data and 0.7729 test data. List the features selected and compare the selected features to those using stepwise regression in task 7. Comment on any differences. So here are the features that are selected, and if you compare these to the features used in task 7. In task 7, we had, it looks like the same features, right? Because we didn't remove any variables. See, there's age, the coefficient is negative and about the same size. For age squared, the coefficient's a little bit smaller. For EDU years, where's EDU years? There it is, 0.0288. So it looks like the Lasso coefficients are consistently smaller. Like, for instance, on age, it's negative 0.78, basically. And on the elastic net, it's negative 0.05, right? This doesn't always appear to be the case, though. Like, for PC1, it's about negative 0.67, and for PC1 here, it's about 0.67, 0.68 almost. So most of the time, the individual coefficients are smaller. This model uses the same variables as the GLM from task 7. However, the coefficients are smaller most of the time in terms of absolute value. For age, the GOM has negative 0.08, but this is negative 0.05. This is because the algorithm shrinks the coefficient. The signs are always the same. For instance, age is negative. Housing, yes, both negative. Task 10, 7 points. Construct a decision tree. Note that the code does not use the constructed PCA variables or the square of age. Instead, 3 of the underlying variables are used. Let's look at the code. This says load the RPart and the RPart plot library, and then the formula says age uses the predictors age plus job plus marital. So I notice that there's no age squared here. There's no principal component. So I run this code and I can see a decision tree. The first part is justify the choice of using underlying variables instead of the constructed PCA variables. So decision trees perform variable selection automatically. This means that the correlated variables that were used in the principal component analysis can be used separately without causing problems in the model. For GLMs, including variables which have a high correlation leads to instability. But this is not an issue for tree-based models. So using these variables also has the benefit of making the tree easier to interpret. 2 of them, irate and employment, are very highly correlated. Your assistant recommends that you only use irate. Justify the elimination of employment. So let's look at the data dictionary again. So irate is a short-term interest rate at the time of the call. Employment is the number of employees of ABC Insurance at the time of the call. One reason, so there may be multiple ways of answering this question correctly. One way that you could do so is to say, one reason for eliminating the employment variable is due to the fact that a customer does not know what the employment is just based on the call. And so this is unlikely to influence their purchasing decision. You could also say something like, one reason for using irate instead of employment is that when interest rates are high, the economy will be healthier, and there will likely be more employees working for ABC Insurance. Better reason, though, is that we are interested in how the results will be used. Because I want these results to be useful for the marketing team at ABC Insurance, I choose to remove employees and to use iRate instead. This will help them to take the interest rates into consideration as they help their sales team to sell the insurance products to customers. So it may be that when the interest rates are high, the people are more likely to save, to not rely on insurance. But when interest rates are lower, there's a smaller incentive for customers to rely on their own savings, and so they may be more open to purchasing insurance. Explain why adding age squared will not improve the decision tree. So go back to the data visualization, and you can imagine that a decision tree would just have different cut points for age. These were at about 25 and 40 to capture the nonlinear relationship. So decision trees automatically capture nonlinear relationships. For the age variable, the tree can use cut points at about 25 and 40 to so that the prediction is higher for customers under the age of 25, lower for those between ages 25 and 40, and then higher. The age squared variable was only needed for the GLM, which does not capture these nonlinear trends. Use the parameters provided in the code chunk to ensure that excess runtime is not used. Run the code without changes. Plot the ROC curve and calculate the AUC on the train and test sets. Discuss any differences in these between the train and test sets and what they signify. So let's look at the ROC curves. Here's the training set and the test set. And I'm trying to make these graphs appear side by side, but it's not working, so I'll just leave them like this. The training AUC was 0.7783. Test AUC was 0.7634. So this is a difference of 0.01 approximately. Compare that to the difference earlier, 0.78 versus 0.77. It looks to be about the same. So this is good. If the tree were overfitting, then the AUC on the test data would be much lower than on the training data. So these still are not as good, though, as the elastic net, which had an AUC of 0.77, is not as good as the elastic net, which had a test AUC of 0.77. One trivia fact about decision trees is that transformations of variables that are monotonic make no difference in the decision tree structure. So an example would be taking the square of age. If I take age squared and then look at this tree, so this is the tree with or age by itself, and then this is the tree with age squared, and you can just see that these are exactly the same, right? And that's because the split points for age squared are just adjusted instead of, so like if let's say you had a split at age is less than 5, well the tree with age squared would just split at less than 5 squared, right? And you can actually do the same, not with just a square transformation, but things like log, right? Because log is also a monotonic transformation. And so, see, this tree is even the same. This tree on the left uses the log of age. This tree on the right used age by itself. And that's because it only takes into account the rank ordering of the values of the predictive variables. And this is useful to know for JBMs and for random forests as well. Candidates need to have considerations related to the use of a decision tree when justifying the variables to be used. So this is referring to part 1 of the question, which is justify the choice of using underlying variables instead of the constructed PCA variables. So the answer that they want is that when you use a decision tree, it automatically removes the correlated variables. One detail which I failed to admit was this comment about the shape of the AUC curves. This says that an AUC, in general, higher probabilities of purchase predicted on the test data by the model fitted on the trained data correspond to higher purchase rates, and lower probabilities correspond to lower purchase rates. Tiny exceptions can be seen in the ROC curve, where the convexity is briefly positive. You can see here that the convexity is briefly positive, meaning that see the curve is up. It's positive but decreasing, positive but decreasing. The slope is positive but increasing right here. So I believe that that's what the comment is referring to, which I didn't pay attention to. So notice that's not the shape on the training data, but it is on the test data. Task 11, 9 points. Employ cost complexity pruning to construct a smaller tree. Review the complexity parameter table for this tree. State the optimal complexity parameter and the number of leaves that will result if the tree is pruned using that value. Let's look at the code for task 11. Here's the CP table. Let's copy and paste this into our document. And so this shows the model's complexity parameter as well as the number of splits in the tree and the error, this X error column. If you don't remember what any of these are, you can just go into your R console and then type in $rpart.control, and then you can read the documentation. It'll tell you what the CP value is. This is the complexity parameter. Any split that does not decrease the overall lack of fit by this factor CP is not attempted. So the question was, review the complexity parameter table, state the optimal complexity parameter will result. You want to minimize this X error column. So I see that it goes 0.62, 0.56, 0.56. It looks like it's lowest at 0.5338, which is that row right there. The table below shows the tree's complexity parameter and the number of nodes, branches, along with the misclassification error. The CP parameter controls the height and variance of the tree. So any split which does not decrease the error by a factor of CP is not used. Let's see if I got that definition right. Any split that does not decrease the overall lack of fit by a factor of CP is not attempted. Any split which does not decrease the overall lack of fit by a factor of CP is not used. There are 12 different trees fit, one for each row. The one which had the lowest error uses a CP of this 0.00063, which has 14 splits. And it says prune the tree using a complexity parameter that will result in 8 leaves. So this would result in 14 leaves, but that would be, as you can see, rather difficult to interpret. So instead, we're going to say CP is equal to this value. Actually, let me try that again. If I use that value, I'll get 14 leaves. So if I use this value, 0.0023, then I would get 8 leaves. And let's check if that's the case. No, that actually doesn't appear to be the case. I see that there are a lot more than, well, there's 1, 2, 3, 4, 5, 6, 7, 8. Yeah, definitely more than 8. So let's try higher value. So that's 1, 2, 3, 4, 5, 6, 7. Wait 1 minute. Let's try this again. That was 0.003. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so this has 10 leaves. What, does it say leaves or branches? It says that will result in 8 leaves. So the leaves are the terminal nodes here. So I want to use this value, 0.0037. It says 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, let's try a value that's slightly higher. This has 1, 2, 3, 4, which isn't enough. So let's go back to 9, because 9 is closer to 8 than 4 is. You could even try testing out like in between values of CP, but for the purposes here, let's just move forward. So let's put this into our document. So I tried to find the tree which had 9 leaves. This means that there were 9 different terminal nodes. The CP table above suggested that this should be when CP is equal to 0.0023. That would result in 8 leaves. But this has 1, 2, 3, 4, 5, 6, 7, 8, 9. However, this was making a tree that had more. I needed to increase the CP to make to 0.003, which was the next highest value on the table below and the table above, which resulted in 9 leaves. To be more precise, I could use a value between 0.00235 and 0.00377 to get a tree that had exactly 8 leaves if I had more time. That's important to note if you run into a task and you know how to get the answer, but you don't have time in the given exam. Just tell the exam grader that, and they will give you partial credit for that question. Oh, and they actually say, if 8 is not a possible option, select the largest number less than 8 that is possible. What are the leaves? The leaves are the endpoints of the tree. If you think about this upside down, so that on the bottom you have the roots of the tree and then the branches going up, just remember that at the very top you'd have the leaves. These are just the terminal nodes of the tree. So in this case, we want a tree that has 8. Like this tree has 1, 2, 3, 4, 5, 6, 7, 8, 9. We want specifically 8 or less than 8. So if I just try using a higher value of CP, like this says that if I use 0.0023, I'll get 8 splits. Let's try a value of 0.003. That will give me 7 splits. Note that splits are different than leaves. Splits are the internal nodes, and leaves are the terminal nodes. So let's just say that I use CP 00037. When I do this, I get this tree, which has 1, 2, 3, 4, 5, 6, 7, 8, 9 terminal nodes. I want less than or equal to 8. So let's use an even higher value. This has 1, 2, 3, 4, 5, 6, which is less than or equal to 8. So let's use this tree. So I tried to find the tree that had 8 leaves. These are the terminal nodes of the tree. The table above shows the number of splits, which are the internal nodes. I increased the CP parameter to make the tree simpler and reduce the number of leaves. I found that by setting CP to be 0.006613, I get this tree, 1, 2, 3, 4, 5, 6 leaves. I tried the other higher values in the table, but these had more than 8. Consider the 2 leaves from the pruned tree that account for the largest proportion of the sample. State 2 insights they give, if any, about marketing the insurance product. So first of all, what are the leaves again? Remember, these are the end nodes of the tree. If we flipped our tree upside down, the leaves would be at the top. And so on this tree, you can read the purchase rate as this middle number. It starts out at 0.47, and then the percentage of patients is this second number. So the 2 leaves which have the highest percentage of patients are this leaf on the far left, which has 52% of all of the patients, and then this leaf has 0%, this leaf has 12%, and the leaf on the far right has 25%. So the tree above shows the purchase rate as the middle number of each node. This starts out at 47% for all patients. The bottom number is the percentage of patients. I see that the leaf on the far left accounts for 52% of all patients, which is a lot. So this is when the interest rate is greater than 2.5%, and when the month is August, so it's June, July, or May, June, July, or August, May through August, or November and December. These patients have a low purchase rate, 25%. And then consider the leaf on the far right. These patients have a purchase rate of 85%. In contrast, the leaf on the far right accounts for 25% of all patients. These people have a purchase rate that is higher at 85%. This is when the interest rate is below 2.5% and the month is April or May. So when ABC Insurance is marketing their products, they should prioritize customers during April and May when interest rates are below 2.5%. And they should avoid calling customers when interest rates are above 2.5% and during the months of May through August or November or December. Task 12, choose a model. This question is only worth 4 points, so I want to go through this very quickly. Select one of your models from tasks 7, 9, 10, or 11. And use for advising the marketing department. Explain your choice. So let's just quickly go back to task 7. Task 7 was a GLM that used age and age squared. So let's just create a quick table because we'll want to show the AUC values. So in task 7, we had the GLM with age and age squared, and that was the test AUC, 0.774. And then in task 9, we had an elastic net with the same variables, but the coefficients were slightly smaller. This has a slightly lower test AUC, 0.7729. And then in task 10, there was the decision tree. This had a test AUC of 0.7634. So this was the pruned decision tree in task 10. This was 0.7634. And then what about task 11? On task 11, we used, so I guess in task 10, this was the tree before pruning, test AUC 0.7634. And then task 11 was the pruned decision tree. So this is a slightly worse AUC of 0.7613. So if we were just choosing our model based on the performance, we would just choose the one that has the highest AUC, which would be this first GLM. This has a lot of variables, and so it will be complicated to interpret. Because the goal is just to find insights, the simplest tree to understand is this tree. Remember that this other tree from task 10 had a high AUC, but it had about 14 different nodes, so it would have been very difficult to explain. So I recommend using the prune decision tree from task 11. This is the highest, has a reasonably high AUC, and more importantly is straightforward to interpret. The GLM has the best AUC, but has a large number of variables, including a principal component. The elastic net has the same variables. Same problem with the large number of variables. The unpruned decision tree had 14 nodes, which was too many for the marketing department to understand easily. So the pruned tree strikes a balance between predictive accuracy and ease of interpretation. Some candidates did not consider both predictive power and applicability to the business problem, and others gave justifications based on one of these, but then chose a model based on the other. So it's really important to answer the question that they're asking for. And I know I keep saying this repeatedly, but here they're asking for a model that gives you predictive insights. And so you should choose a model that does so. Note that because their elastic net performed variable selection, it resulted in a simpler model, and that's the result that they recommend. However, in this solution, we found that the pruned decision tree was easier to interpret while still giving high predictive power, and so this was our choice. It doesn't say anywhere in this solution that you would need to choose the elastic net, right? It just says you needed to consider predictive power and applicability to the business problem. And these questions are designed to be graded independently of one another. So the exam grader would look at your table here, it would look at your values of your AUC, and they would consider the interpretability. And they would expect you to make a good choice based on this information in the problem. Task 13, 20 points. Write an executive summary. Your executive summary should reflect the information provided and work from tasks 1 to 12 as relevant to the marketing department. The executive summary should include a problem statement, discussion of data, a coherent explanation and justification of your recommended model, and conclusions. Be sure to include recommendations regarding future marketing efforts from the model chosen in task 12. You can avoid writer's block by remembering a simple formula that is ROID. This stands for Reader, Objective, Issue, and Data. The reader, in this case, who is the audience? That is the ABC. So if you go back to the project statement, you can see ABC Marketing Department. So the marketing department at ABC Insurance, and then objective is either inference, which is trying to understand the problem, or prediction, which is making really accurate model estimates. This question is, for a variety of calls collected, they would like you to advise them on future campaigns. Has requested that we assist them with their phone call marketing campaigns. And the issue is improving the conversion rates. That is increasing their profits by having more customers purchase their products. We are helping them to increase their profits by improving their conversion rates. That is the percentage of customers who purchase a product after being called. And in addition, we are interested in increasing the amount of coverage which customers purchase. And then data is, so your task is to use available data, and there's a footnote. So this is the bank marketing data set from 2014. Using predictive analytics and data from 2014, which contains phone call info. This report seeks to help to, let me say this again. We are helping them to increase their profits by improving their conversion rates. That is the percentage of customers who purchase a product after being called. In addition, we are interested in increasing the amount of coverage which customers purchase. Using predictive analytics and data from 2014, which contains customer phone calls, this report helps to increase profitability in this way. So let's go into more detail. So for each phone call, which is how many records are in the data. Well, originally there were more. Remember, because we had to remove records. So let's go back up to the initial data. I don't want to overwrite it. So let's just call this DF2. There were 10,000 records. For each of the 10,000 phone calls, we have info regarding the customers, and what are the columns? Customers' demographic, such as their age, educational years, marital status, job, housing, loan history, the month and weekday of the call, type of phone, and the state of the economy. We are given whether each customer purchased an insurance product or not. So now let's split the windows so that I can go back up to the beginning. And I'd like to start off by just going right into the model interpretation and then talking about the all of the details of the data manipulation and so forth later. So the decision tree, right, was the model that we chose. So let's interpret that. So this is our decision tree. So the following formula tells whether or not a customer purchases. So is the interest rate less than, so let's begin on the top and then work down here. So is the interest rate above 2.5%? If yes, then is the month June through August or November through December? If yes, then the purchase rate is very high. Let's make that bold. At, I'm sorry, not very high, very low, at 25%. This represented 52% of all customers, meaning that when the interest rates are high or during the summer, ABC should not spend their resources on calling customers. If no, then you can actually look and say there are actually 0% of customers here, so you can just skip this node. And now let's consider this node, which is 12%. So is the interest rate greater than 25%? If no, then for April and May, purchase rate is very high at 85%. ABC should prioritize calling customers when the interest rates is low and during these peak months. In other words, you could just say during April or May, and then let's look at this node. If the CPI is more than 93, the purchase rate is, let's just say high at 66%. Let's just fill out the other ones. When the CPI is less than 93, and now we just have these two nodes. When the interest rate is less than 1.3, then the purchase rate is, let's just say medium, moderate, moderate. And then otherwise, the purchase rate is low. So moderate here is actually, this is actually a higher purchase rate because this is 66%, this is 72%. So let's call this is also very high at 72%, right? And then otherwise the purchase rate is low, 40%. And these high, low, moderate are just subjective measures. You could use other words for the same things. So I'm just using very high, high, and low. I could even just simplify this. Let's just use low and high. Let's just see if this is readable. I would just maybe simplify this and say during June through August or November through December. Now we're going to delete this and then move this up one. And then say there were few customers who were recorded in other months, but those who had a high purchase rate. And that's this group right here. And then let's simplify this. So then this is asking about the interest rate again. The following formula tells whether or not a customer will purchase. And don't worry about all of these markups, these pen markings. These are just for the lesson video. These wouldn't be included in the actual report. So just ignore them when you're writing your document. So moving on, we've looked at some observations. We also looked at the education variable. We just converted this. Well, we just said if it is a factor, it would have to have different values. Okay, so for the education variable, so say we found that a person's education level was important to consider. However, in the data that was provided to us, it was given as a discrete value. That's being too technical. We found that a person's education level was important to consider. Not only does one need to take into account the type of education, but the number of years as a numeric years, including middle school, college, and postgraduate studies. All of these add up. So for each person, we calculated their total years of education and used this in the model, in the analysis. And we talked about missing values. So there were missing values present that needed to be fixed. So for EDU years, we saw that there were 5% missing, and so I imputed the mean, which means I just replaced the missing values with the mean. For housing, 2.5% of cases, I just removed these values. For job, I was missing. So in some cases, it was acceptable to simply remove the records which had missing values. But in other cases, this would have introduced survivorship bias into the analysis. In this context, survivorship bias would be failing to consider what happens to customers who were not included and basing the results only on those who were. For example, customers who are given bad customer service may hang up the phone early and thus never have their information recorded. These would be a lost sale for ABC Insurance, and so would not want to miss out on this information. To address this issue, we only removed values when we deemed that they were missing because of random chance and that the number of customers impacted was small. As an alternative, we filled in numeric values using the average and replaced categorical records using a special category. And then maybe just summarize. So the records which had missing values were EDU years. Yeah, actually, that's probably enough. I don't need to go into more detail. It says in the project statement not to just repeat what you've already said, but to try to be more abstract in your writing. And then investigate correlations. So what did we do? We compared the correlations of the economic variables. So how do you say this? We helped ABC Insurance to simplify their data by conducting a correlation analysis. Two things are correlated when an increase in one or tends to accompany an increase in another. A decrease in one thing tends to accompany a decrease in the other thing. This data contained several measures of the state of the economy, such as the Consumer Price Index, CPI, Consumer Confidence Index, short-term interest rate. We confirmed that there is a correlation between I rate and the number of employees of ABC Insurance, and then the other high correlation was I rate and CPI, and I rate and CPI. And then just say if ABC Insurance is interested in these details, see the body of this report, which contains the calculated correlations. And then also say we considered, no, that's probably enough. Okay, conduct principal component analysis. So let me go even further back. Let's say there is danger in using variables which are correlated directly in models. One way of addressing this problem is with a principal component decomposition. So this merges together variables which are correlated into new simpler variables, into fewer variables, which contain the same information, most of the same information. We use this method to combine the economic variables into a single index, a numeric measure of the economy, which ABC can use in their analysis. We tested our models using both this new index as well as the original variables. The advantage to using the index is that the models may be more reliable. The disadvantage is that they are more difficult to understand. And then we created a generalized linear model. So this is one of the boilerplate sentences is as follows. To ensure that the results of this study can be reproduced in real life, we split the data into two groups. A training group where the models were built and a testing group where the models were evaluated. There was no overlap between these groups of customers, so that you could simulate how reliable the results will be on new data. We looked at several different types of models, and then these were GLMs, generalized linear models, GLMs with stepwise selection, GLMs with penalized, with shrinkage, decision trees, pruned decision trees. And so we looked at each type of these models and considered their advantages. So for GLMs, generalized linear models, just to add some bullet points here, we found that we could capture the effect of a person's age. Talking about age and age squared is probably too detailed. It could be more abstract. So we found this model had the best performance, but was also the most difficult. Let me just say, we found that a person's age is predictive of whether they will purchase or not. This model, okay, so we looked at age, we looked at the AUC, moving on. There's the PCA. So to simplify, we tried making the model, the above model, simpler using a method known as stepwise selection. This made the model simpler right here, and actually could be considered as an alternative to the decision tree. So one of the advantages to using this model would be that there would be a gradual change in the customer's. Now let me just, so you were basically trying to predict whether or not the customer will purchase or not. So if you use a GLM, instead of getting let me just go back. For any of these models, I can just look at the cheat sheets. Advantages and disadvantages of a generalized linear model. This would be, it's still easy to interpret. It can also be deployed in a spreadsheet. Some disadvantages would be, it doesn't do a good job of handling the uncorrelated variables, right? Because this GLM used the principal component analysis. So one advantage to this model is that it can be explained in a spreadsheet. One disadvantage is that it used the results of the principal component analysis, and so was complex to understand. And then we looked at the GLMs with shrinkage, and remember, this didn't work because it didn't remove any of the variables that we wanted it to. The idea behind this model is that it could simplify the results by removing variables. However, in this case, we did not find that any variables were removed. And then the decision trees, let's go down to the decision tree part. Here's our decision tree, but remember, it was too complicated because it had 20 nodes or something like that. We fit a decision tree. Let's just say the first trees that we fit were too complex to understand, although they were being too sensitive to the data which we used to build the trees, and were not finding patterns in the data which would generalize to new data. In other words, this was overfitting. Then the prune decision tree. This model struck a balance between good performance, AUC of, what was our final AUC? Decision tree, 0.7613. Good performance while also being explainable in the above table. And it handles low quality and complex data automatically, which can be useful for future studies. In this context case, we needed to replace missing values by hand, and to look for complex data relationships by looking at graphs which was time consuming, right? By using a tree-based approach model, we could perform these steps quickly when looking different customers. At this point, I want to start wrapping up. So I'll get rid of this split and then think about writing a brief conclusion. So I'll say something like, in conclusion, this report shows that using predictive analytics, you can certainly guess whether a customer will purchase or not before making the phone call. So as a marketing manager, you can examine the customer's demographic data as well as the situational and as well as the environment, and use this to optimize your conversion rates. It's also worth mentioning limitations. So I like to say the results of this study were based only on limited data from the year 2014. And so if the results need to be applied to later years, then new data will need to be supplied and this analysis updated. We assumed that the records which were removed were missing randomly. If there was a pattern behind whether these values were missing, this could materially change the results. Think about other assumptions or models. We considered only specific parameters of the different models. We didn't do a hyperparameter tuning. We did on the decision tree, and we did on the lasso, actually. Yeah, I think that's any other major assumptions. Well, we assume that this data will be consistent in the future and that the way that people answer phone calls will not change. When answering the phone, the way in which a question is asked can have a big impact on the answer. So we assume that ABC's phone call strategy, tactics, will not change. If this changes, then the results will no longer apply because the underlying data would be different. So now when I still have a few minutes left, I want to go back and just review because a component of their grading is based on the overall professionalism, the spelling, grammar, and so forth. So I'll just go through and make these suggested edits. So I just right click and then approve the edit. Again, these drawings are not going to be included in the actual report. They're simply shown here for illustrative purposes. Our executive summary was materially different than the SOA's solution. This is because we used a different model. However, both of our executive summaries, I think, were sufficient in order to get a full 20 points on the question. Some of the key differences, though, were the way that the SOA interprets the elastic net. This is in the form of an odds ratio. This is more difficult to interpret than using a simple decision tree because the output, again, is the odds, which is the probability of the customer purchasing divided by the probability of them not purchasing. And so this would be somewhat cumbersome to explain. It's interesting that they say, I will provide a spreadsheet that carries out this calculation. Provide the details above to specify which situations are expected to have positive or negative impacts on the purchase rate. You can attach Excel files to your solution. So if you do calculations on the side, it's worth including that as a spreadsheet and then make a note in your report. We found similar themes for the timing of month interest rates and employment. We both have had the same findings for job and education level, targeting retired and student prospects. Areas where I think my report was different were, first of all, I made some simple mistakes in the formatting. Here I said I could revise this sentence structure. I should break this up into 2 sentences here. So I'll say, we are helping them to increase their profits by improving their conversion rates, period. This is the percentage of customers, etc. So I might lose points for that grammar. Also, there's a formatting mistake here. I have an extra line, and I could say the following formula tells whether or not a customer will purchase, which Microsoft Word is flagging as being a grammatical error. I actually think that that's okay. Other things to note are that I go into detail about the survivorship bias case, which is unique, right? You won't find something like this in the SOA solution. In your exam, you might find something different, right? So don't be afraid to follow your intuition when you're making recommendations. Be creative. Use your real-life actuarial experience, and I don't think that the SOA is expecting everyone to write the exact same executive summary. I think they're expecting you to demonstrate that you use the analytical tools to come up with useful findings, whatever those may be. The solution does also say that you shouldn't go into detail about brief discussions and approaches attempted are acceptable, but candidates should avoid lengthy discussion about modeling techniques that were not ultimately selected. This is probably an area where I would lose points because I have this discussion about alternative models, which the client really wouldn't care about because they're not a modeling team, they're a marketing team. So this would cost me a lot of time and probably would have lost me points.